Picture this. You're standing in your room right now, and photons, particles of light, are streaming past you from your screen, your lamp, bouncing off every surface. These photons have absolutely zero mass. Nothing. Not even a billionth of a gram. They're pure energy, racing through space at the fastest speed anything can possibly move. Now here's what's going to shatter everything you think you know about reality. Despite having zero mass, light bends. It curves. It follows paths that arc through space like a marble rolling around the inside of a bowl. And the thing making it bend? Gravity, the same force that supposedly only pulls on things with mass. This isn't science fiction. In 1919, a British astronomer named Arthur Eddington traveled to a remote island off the coast of Africa during a total solar eclipse and photographed stars near the sun. Those stars appeared shifted from their actual positions. The light from those stars had bent around the sun on its journey to Earth. This single observation proved Einstein right and Newton wrong, and it revealed something so profound about the nature of reality that we're still grappling with its implications today. If gravity only attracts mass, and light has no mass, then what you just learned should be impossible. But it happens. Every second of every day, all around you, light is bending through the universe's gravitational fields. This isn't a minor detail. This is a fundamental crack in how we understand reality itself. What if I told you that gravity isn't actually a force at all? That the universe isn't what it appears to be? And that understanding why light bends will reveal that space and time aren't separate things, but a single flexible fabric that's being warped right now, in this very moment, by your own body? But before we go further, smash that like button and subscribe to this channel, because we're about to take you on a journey that will fundamentally change how you see the universe. Drop a comment telling me what country you're watching from, and what time it is where you are. Want to know where in the world minds are being blown right now? Let's build a global community of people who aren't afraid to question everything. For thousands of years, humans looked up at the night sky and saw order. The stars moved in predictable patterns. The planets traced paths across the heavens. Everything made sense because everything seemed to follow rules. Then in 1687, Isaac Newton published his law of universal gravitation, and suddenly we had the mathematical language to describe what we'd been observing. Newton's equation was beautifully simple. The force of gravity between two objects equals the gravitational constant times the product of their masses, divided by the square of the distance between them. F equals g times m divided by r squared. Look at that equation closely. See those m's? Those represent mass. Newton's gravity explicitly requires mass. Two masses attract each other with a force proportional to how massive they are. A bowling ball and Earth attract each other more strongly than a marble. And Earth, because the bowling ball has more mass. Makes perfect sense, right? This worked brilliantly for over 200 years. We predicted planetary motions, calculated the mass of celestial bodies, sent rockets to the moon all using Newton's equations. Gravity was this invisible force reaching across space, pulling massive objects toward each other. But there was always something weird about light. In the early 1800s, scientists were having fierce debates about what light actually was. Some, like Thomas Young, believed light was a wave. He proved it with his famous double-slit experiment in 1801, showing that light creates interference patterns, just like waves in water. Others believed light was made of particles, tiny bullets of energy shooting through space. Here's where it gets interesting. If light is made of particles, those particles should have mass, right? And if they have mass, Newton's gravity should affect them. A few scientists, including Newton himself, actually speculated about this. But when they did the calculations, the amount light should bend according to Newtonian gravity was incredibly tiny, so small it seemed impossible to measure. But if light is a wave, as Young's experiment suggested, then what is it waving through? Scientists invented this substance called luminiferous ether, an invisible medium that supposedly filled all of space and allowed light waves to propagate. Think of it like water for ocean waves or air for sound waves. Light needed something to wave through. In 1887, two American physicists, Albert Michelson and Edward Morley, set up an incredibly sensitive experiment to detect this ether. The idea was simple. If Earth is moving through this cosmic ether, then light should move at different speeds, depending on whether it's moving with or against the ether wind. Just like sound travels faster downwind than upwind. They measured nothing. Zero difference. The speed of light was exactly the same in all directions, regardless of Earth's motion through space. The ether didn't exist. This was a crisis. How could light be a wave if there was nothing for it to wave through? And how fast was light actually moving? The answer to that second question came from a Scottish physicist named James Clerk Maxwell. In the 1860s, Maxwell was working on unifying electricity and magnetism into a single theory. When he wrote down his equations, now called Maxwell's equations, something extraordinary fell out of the mathematics. His equations predicted that oscillating electric and magnetic fields should create waves that propagate through space. And when he calculated the speed of these waves, he got roughly 300 million meters per second. That was the speed of light. Maxwell had just discovered that light itself is an electromagnetic wave, a self-propagating disturbance in electric and magnetic fields that doesn't need any medium to travel through. Light doesn't wave through anything. It just waves. Now here's what Maxwell's equations also told us. The speed of light is constant. Not just approximately constant, but fundamentally, universally, absolutely constant. No matter how fast you're moving, no matter what you're doing, you will always measure light traveling at exactly 299,792,458 meters per second. Think about how bizarre that is. If you're standing still, and I'm running toward you at 10 meters per second, and we both measure the speed of a car driving toward us, we'll get different answers. You might measure the car going 30 meters per second, while I measure it going 20 meters per second, because I'm already moving 10 meters per second toward it. That's common sense. But light doesn't work that way. If you're standing still, and I'm racing toward you at half the speed of light, and a beam of light passes us, we will both measure that light traveling at exactly the same speed, the same number. That shouldn't be possible, but it is. This created an absolutely monumental problem for physics at the turn of the 20th century. Common sense says that speeds should add up. The math says they do. But light refuses to follow the rules. Enter Albert Einstein. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would change everything. Albert Einstein looked at the problem everyone was struggling with. How can the speed of light be constant for all observers? And realized that everyone was asking the wrong question. The real question wasn't, why doesn't light speed up or slow down? The real question was, what has to be true about the universe for light's speed to be constant? His answer was shocking. Space and time themselves must be flexible. Here's Einstein's thought experiment. Imagine you're on a train moving at a significant fraction of the speed of light. You turn on a flashlight pointing forward. Common sense says the light should be traveling at the speed of light plus the train's speed, right? Like throwing a ball while running, the ball moves faster than your running speed. But that can't happen. Light must travel at exactly the speed of light for you, and for someone standing on the platform watching the train pass. So what gives? Time gives. Literally, Einstein realized that time must be passing slower for you on the train than for the person on the platform. From your perspective, time is normal, and you measure light going the speed of light. From the platform's perspective, your time is slowed down, which means your measurement of speed, which is distance divided by time, gives you the same answer even though you're moving. Space gives too. Lengths contract in the direction of motion. The faster you go, the more space squishes in front of you. Your train actually becomes physically shorter from the perspective of someone watching it pass. This is called special relativity, and it's not a theory about light, it's a theory about space and time. Light's constant speed isn't the conclusion, it's the starting assumption. The conclusion is that space and time are not absolute, fixed stages on which events happen. They're relative, flexible dimensions that change depending on how fast you're moving. Now, this is already mind-bending enough. But Einstein wasn't done. Special relativity only dealt with objects moving at constant speeds and straight lines. What about acceleration? What about gravity? This bothered Einstein for years. Then, in 1907, he had what he later called the happiest thought of my life. He was sitting in his office at the Patent Bureau, and he imagined a person falling off a roof. While falling, that person would feel weightless. They wouldn't feel gravity at all. From their perspective, floating in mid-air, they're not accelerating, they're just existing, and the ground is rushing up to meet them. Now imagine an astronaut floating in deep space, far from any gravitational field. They too are weightless. From the astronaut's perspective, there's no way to tell the difference between falling freely in a gravitational field and floating freely in empty space. This is called the equivalence principle, and it's the foundation of general relativity. Einstein realized that gravity and acceleration are two ways of describing the same phenomenon. Being in a gravitational field is equivalent to being in an accelerating reference frame. But here's where it gets truly revolutionary. If gravity and acceleration are equivalent, and if acceleration affects space and time, which special relativity proved it does, then gravity must also affect space and time. Think of it like this. Imagine you're in an elevator in deep space with no windows, accelerating upward at exactly the acceleration of Earth's gravity, 9.8 meters per second squared. You're pressed against the floor, just like you are standing on Earth. Now, imagine you shine a laser pointer from one wall to the other. From your perspective in the accelerating elevator, the light beam curves downward, because while the light is traveling across the elevator is accelerating upward, so the far wall moves up to meet the beam. But if acceleration curves light's path, and if acceleration is equivalent to gravity, then gravity must curve light's path too. This was Einstein's stunning insight. Gravity doesn't pull on light, despite light having no mass. Gravity curves the space through which light travels. Light always travels in straight lines, but in curved space, straight lines are curved. Let me say that again, because it's crucial. In Einstein's view, light isn't bending. Light is going perfectly straight. Space itself is bent. Now we need to understand what curved space actually means, because this is where things get truly wild. First, forget about space and time as separate things. Einstein showed they're intimately connected, so much so that physicists now talk about spacetime as a single four-dimensional entity. You're not just moving through space, you're moving through spacetime. Every path you take is a path through both space and time. Think of it like this. When you walk from your kitchen to your bedroom, you're obviously moving through space, but you're also moving through time. It takes you, say, 10 seconds to make that walk. Your path isn't just a line through your house. It's a path through space-time that includes both the spatial distance and the temporal duration. Now, Einstein's insight was that massive objects curve space-time. Imagine space-time as a stretched rubber sheet, a two-dimensional surface representing the three-dimensional space around us. Yes, we're reducing dimensions to make it visualizable. Bear with me. When you place a massive object like a bowling ball on this rubber sheet, it creates a depression, a curve in the sheet. Now roll a marble across the sheet. If the sheet is flat, the marble goes in a straight line. But if the sheet is curved by the bowling ball, the marble's path curves too. Not because anything is pulling on the marble, but because it's following the straightest possible path through curved space. This is what's happening with light and gravity. The sun, Earth, black holes, all massive objects curve the spacetime around them. Light always travels along what's called a geodesic, the straightest possible path through spacetime. But when spacetime is curved, those geodesics are curved too. Here's where your mind should start bending. What we perceive as gravity is actually the curvature of spacetime. When you drop a ball, it's not being pulled downward by a mysterious force. It's following the curved geometry of spacetime created by Earth's mass. The ball is actually moving in a straight line through curved spacetime, and we perceive that as falling. You right now, sitting or standing wherever you are traveling through time at 1 second per second. That's your default motion through spacetime. But Earth's mass curves the spacetime around you, which means your path through time is slightly tipped toward Earth's center. You experience this tipping as gravity, as the sensation of weight, as the need to hold yourself up. If you could view the universe from outside spacetime, which you can't, but let's imagine, you'd see that you're not standing still. You're constantly being accelerated through spacetime by the curvature created by Earth's mass. The floor beneath you is pushing up against this natural motion, which is why you feel pressure on your feet. Einstein spent the better part of a decade, from 1907 to 1915, working out the mathematics of this. The final equations of general relativity are extraordinarily complex. They involve tensors, which are mathematical objects that describe how spacetime curves in response to energy and momentum. The full equations require advanced calculus and differential geometry to even write down, let alone solve. But the conceptual core is beautiful. Matter and energy tell spacetime how to curve, and curved spacetime tells matter and energy how to move. That's gravity. Now, here's what will blow your mind. Light doesn't just travel through curved spacetime. Light itself contributes to the curvature. Remember when I said light has no mass? That's true. But light does have energy, and Einstein's famous equation E equals mc squared tells us that energy and mass are equivalent. They're two forms of the same thing. In Einstein's field equations, it's not just mass that curves spacetime. It's the entire energy-momentum tensor, which includes mass energy, momentum, pressure, and stress. Light carries energy and momentum, so light itself curves spacetime. The effect is incredibly tiny. A beam of light from a laser pointer curves spacetime by an immeasurably small amount. But in principle, if you had an intense enough beam of light, you could create a gravitational field with no mass whatsoever. Some theoretical physicists have even speculated about Causality black holes made purely from trapped light, with no matter involved at all. So Einstein had this radical new theory. Gravity isn't a force. It's curved spacetime. Light bends not because it's pulled by gravity, but because it follows curved paths through warped spacetime. This explained all the same phenomena Newton's gravity explained, but with a fundamentally different mechanism. But was it true? Science isn't philosophy. You need evidence. Einstein made 3 predictions that differed from Newton's gravity, 3 tests that could prove or disprove his theory. First, he predicted that Mercury's orbit should precess, that is, slowly rotate in a way that Newton's equations couldn't fully explain. Astronomers had actually observed this precession for decades and couldn't account for it. Some even proposed there was another planet closer to the Sun, which they called Vulcan, to explain Mercury's strange orbit. When Einstein calculated Mercury's precession using general relativity, he got the exact amount observed. Vulcan wasn't needed. Curved spacetime explained it perfectly. Second, Einstein predicted that light would be shifted toward longer, redder wavelengths when climbing out of a gravitational field. This is called gravitational redshift. Think of it like this. Light climbing out of a gravitational well loses energy, just like a ball rolling uphill loses kinetic energy. When light loses energy, its frequency decreases and its wavelength increases, shifting it toward the red end of the spectrum. This was confirmed in laboratory experiments and later with stellar observations. But the third prediction was the most dramatic: the bending of starlight by the sun's gravity. Einstein calculated that light from a distant star passing near the sun should be deflected by approximately 1.75 arcseconds. That's an incredibly tiny angle, about the width of a human hair, viewed from 3 meters away. But it was measurable with the telescopes of the time. There was just one problem. You can't see stars near the sun during the day because the sun is too bright. You need a solar eclipse. Enter Arthur Stanley Eddington, a British astrophysicist who was fascinated by Einstein's theory. When he learned there would be a total solar eclipse on May 29, 1919, visible from the island of Principe off the west coast of Africa and from Sobral, Brazil, he organized 2 expeditions to photograph stars near the sun during the eclipse. This was just 6 months after World War I ended. Einstein was German. Eddington was British. Testing Einstein's theory was more than scientific, was a statement about international cooperation and the universal nature of truth. The expeditions faced enormous challenges. They had to transport delicate photographic equipment to remote locations, hoping for clear weather during the few minutes of totality. They needed to photograph the same stars at night when the sun wasn't in the way to compare the star positions. On Principe, Eddington's team faced clouds and rain. Only a few usable photographs were captured during brief, clear moments. In Sobral, the other team had better conditions but equipment problems. When Eddington returned to England and analyzed the photographic plates, he found exactly what Einstein predicted. The stars near the sun appeared shifted by about 1.75 arcseconds from their actual positions. Light had bent around the sun. On November 6, 1919, the Royal Society and the Royal Astronomical Society held a joint meeting to announce the results. The meeting was held in the same room where Newton had once presided over the Royal Society. The president of the Royal Society, J. Thomson, who had discovered the electron, declared the findings one of the most momentous, if not the most momentous, pronouncements of human thought. The Times of London ran the headline, "Revolution in Science, Newtonian, Ideas Overthrown." Einstein became an overnight celebrity, perhaps the most famous scientist who ever lived. But here's what's important. This wasn't just confirming a prediction. This was confirming that our fundamental understanding of reality was wrong. Space and time aren't fixed. Gravity isn't a force. The universe is stranger, more flexible, more interconnected than anyone had imagined. And light, massless light, was the key to proving it all? Now that we know light bends in gravitational fields, an obvious question emerges. What if the bending is really extreme? What happens when light passes near something much more massive than the Sun? The answer is one of the most spectacular phenomena in astronomy: gravitational lensing. In 1936, Einstein received a letter from an amateur scientist named Rudi Mandl, who asked whether a star could act as a lens, focusing light from a more distant star behind it. Einstein was skeptical, but worked out the math in a published paper. He concluded that while theoretically possible, the effect would be too small and too rare to ever observe. He wrote, "Of course, there is no hope of observing this phenomenon directly." Einstein was wrong. In 1979, astronomers discovered something remarkable: a quasar, an extremely distant, bright galaxy powered by a supermassive black hole that appeared as two separate images in the sky. The quasar, designated QSOO 957 plus 561, looked like twins. But spectroscopic analysis revealed they were identical. Same light, same spectrum, same variability in brightness. What they were seeing was a single quasar whose light was being bent around a massive galaxy between us and the quasar. The galaxy's gravity was so strong it split the quasar's light into two separate paths, creating two images of the same object. This was the first confirmed gravitational lens, and it opened up an entirely new field of astronomy. Think of it like this. Imagine you're looking through a wine glass at something on the far side of the table. The curved glass distorts and magnifies the image. That's exactly what massive galaxies do to light from objects behind them, except the glass is curved spacetime. Since that first discovery, astronomers have found thousands of gravitational lenses. Some create multiple images of the same object, 2, 4, even dozens of images arranged in arcs and rings around the lensing galaxy. These are called Einstein rings when they form complete circles. The most spectacular examples are galaxy clusters, which contain thousands of galaxies and enormous amounts of dark matter. These clusters create incredibly complex lens systems, distorting entire background galaxies into stretched arcs and multiple images. In 2022, the James Webb Space Telescope captured stunning images of the galaxy cluster SMACS 0723, showing countless arcs and distorted galaxies, all light bent by the cluster's immense gravitational field. Some of those arcs represent galaxies from when the universe was less than 1 billion years old, their ancient light magnified and brought into view by gravitational lensing. But here's what makes gravitational lensing so powerful. It's not just pretty pictures. It's a tool for understanding the universe. First, lensing allows us to weigh galaxies and galaxy clusters with extraordinary precision. By measuring exactly how much light is bent, we can calculate exactly how much mass is doing the bending. This is how we've confirmed that most of the universe's matter is dark matter that doesn't emit light, but does curve space-time. Second, lensing acts as a natural telescope, magnifying distant objects that would otherwise be too faint to see. The most distant galaxies ever observed have been found using gravitational lensing, allowing us to peer back to when the universe was just a few 100 million years old. Third, lensing creates time delays. When a lensed object like a quasar has multiple images, light taking different paths around the lensing galaxy arrives at different times. If the quasar brightens, we see that brightening in one image, and days or weeks later in another image. By measuring these time delays and combining them with models of the lens, astronomers can calculate the expansion rate of the universe, a key number called the Hubble constant. Here's a mind-bending consequence. Because of gravitational lensing, we can sometimes see multiple versions of the same event at different times. If a supernova explodes in a lensed galaxy, we might see the explosion in one image, then see it repeat in another image weeks later as the delayed light arrives. In 2014, astronomers discovered a supernova in a lensed galaxy and predicted when and where its light would appear in other images. Sure enough, In 2015, the replay appeared exactly as predicted. We're literally watching the universe in reruns, thanks to curved spacetime. We've been talking about how gravity curves space, but here's what will truly blow your mind. Gravity curves time even more dramatically than it curves space. And this has consequences you experience every single day. Let me prove it to you. Take out your phone. Check the time. The fact that your phone knows what time it is, with accuracy measured in nanoseconds, depends on understanding how gravity warps time. GPS satellites orbit Earth at an altitude of about 20,000 kilometers. Because they're higher up in Earth's gravitational field, further from Earth's center, time passes slightly faster for them than for us on the surface. We're deeper in the gravitational well, so our time is more dilated, more slowed down. The difference is tiny, about 45 microseconds per day, but light travels fast, really fast, 300 million meters per second. In 45 microseconds, light travels 13 kilometers. If we didn't correct for gravitational time dilation, GPS would accumulate errors of 13 kilometers per day. Within a week, your navigation would be off by more than 90 kilometers. Every GPS satellite carries atomic clocks that are deliberately set to run slower than clocks on Earth before launch, compensating for the time dilation they'll experience in orbit. Your phone right now is performing calculations based on Einstein's general relativity to tell you where you are. Gravity doesn't just bend space, it bends time. This time, dilation gets more extreme the stronger the gravitational field. At the surface of a neutron star or an object, with the mass of our sun compressed into a sphere, the size of a city time passes about 30% slower than it does in empty space. A clock on a neutron star would tick at roughly 70% the rate of a clock far from any gravitational field. Near a black hole, time dilation becomes extreme. At the event horizon of a black hole, time effectively stops from the perspective of a distant observer. If you watched someone fall into a black hole, you'd see them slow down as they approached the event horizon, their movements becoming more and more sluggish, their light becoming more and more red-shifted, until they appeared to freeze in place just outside the horizon, never quite crossing it. But from the perspective of the person falling, nothing special happens at the event horizon. They just keep falling, passing through in a finite amount of their own time. This is one of the deepest paradoxes of black holes. Whether you cross the horizon depends on whose clock you're using. Now here's where this connects to light. Remember, light always travels at the speed of light, but the speed of light is a measure of distance per time. If time is running slower in a gravitational field, and light still has to travel at the speed of light according to local measurements, then something has to give. What gives is the path. Light curves more sharply through regions where time is more dilated. The bending of light isn't just about the spatial curvature of spacetime, it's about temporal curvature too. In fact, for most gravitational fields we encounter, including Earth's and the Sun's, the time component of spacetime curvature contributes more to light bending than the space component does. When you drop a ball, it's mostly falling into the future more than it's falling downward through space. Think about that. Gravity is primarily a distortion of time, not space. This has an almost philosophical consequence. The reason objects fall isn't because space is curved downward. It's because the future is curved toward massive objects. Time itself is flowing differently in gravitational fields, and objects follow that flow. Here's a thought experiment to make this concrete. Imagine you're standing still on Earth. You're aging at a certain rate, 1 second per second by your own clock. But compared to someone floating in deep space, far from any gravity, you're aging slightly slower. Your future is compressed compared to theirs. Now, your head is about 30 centimeters further from Earth's center than your feet. That means time is passing infinitesimally faster at your head than at your feet. Your head is aging faster than your feet. The difference is only a few nanoseconds per year, but it's real and measurable with sensitive atomic clocks. In 2010, physicists at the National Institute of Standards and Technology in Boulder, Colorado, built atomic clocks so precise they could detect time dilation over height differences of just 33 centimeters. They published a paper proving that a clock on a table runs faster than a clock on the floor by exactly the amount Einstein's equations predict. You are literally being stretched through time right now. Your head exists slightly further into the future than your feet. Now let's talk about what happens when gravity gets so strong that light itself cannot escape. Black holes are perhaps the most extreme consequence of Einstein's equations. They're regions where spacetime is curved so intensely that the future itself points inward. Once you cross the event horizon, the boundary of a black hole, every possible path forward through time leads deeper inside. There's no escape, not because you're being pulled inward, but because outward has ceased to exist as a future direction. Let me explain that more carefully, because it's genuinely strange. Outside the event horizon, you can point in various directions through space, toward the black hole, away from it, tangent to it. If you're far enough away, you can fire your rockets and leave. But once you cross the horizon, the direction toward the center of the black hole becomes the future. Not figuratively, literally. Just as you cannot travel backward in time, you cannot travel away from the singularity once you've crossed the horizon. The singularity, the point at the very center of a black hole, where all the mass is concentrated, isn't a place in space. It's a moment in time. It's your future if you cross the horizon, as inevitable as next Tuesday. This has profound implications for light. A photon that crosses the event horizon isn't just trapped. Its future light cone, the set of all possible points it could reach, has been tilted so dramatically that every possible trajectory points inward. The photon must hit the singularity. It has no choice. But here's what's beautiful and terrifying. Before light falls into a black hole, it can orbit it. There's a region called the photon sphere, at 1.5 times the Schwarzschild radius of the black hole, where photons travel in circular orbits. Light going in a circle, not because anything's pulling on it, but because space-time is curved into a shape where circular photon paths are geodesics. If you were somehow able to place your head at the photon sphere of a black hole, you'd be long dead from tidal forces. But let's imagine you could see the back of your own head. Photons leaving the back of your head would orbit the black hole and enter your eyes from the front. Black holes also create an optical phenomenon called gravitational lensing, taken to its extreme. The black hole's intense gravity bends light from stars and galaxies behind it into distorted arcs and rings. If you looked at a black hole against a starry background, you'd see a black disk, the event horizon surrounded by a bright ring called the photon ring, which is actually light from stars behind the black hole that's been bent around it. In April 2019, the Event Horizon Telescope collaboration released the first ever photograph of a black hole. Not an artist's impression, an actual image constructed from radio telescope observations of the supermassive black hole at the center of the galaxy M87, 55 million light-years away. The image shows exactly what Einstein's equations predict: a dark shadow surrounded by a bright asymmetric ring. That bright ring is emission from hot gas orbiting the black hole at close to the speed of light, and the shape of the ring is determined by how the black hole's gravity bends light. One side of the ring appears brighter than the other because the gas on that side is moving toward us at relativistic speeds, causing Doppler brightening. The entire image is a testament to curved spacetime. Every photon captured by those telescopes took a path warped by one of the most extreme gravitational fields in the universe. In 2022, the same collaboration released an image of the black hole at the center of our own Milky Way galaxy, Sagittarius A*. Again, the observation matched the predictions of general relativity with stunning accuracy. But here's where things get truly mind-bending. Black holes don't just bend light, they can amplify it. When matter falls into a black hole, gravitational energy is released, lots of it. The accretion disk around a supermassive black hole can shine brighter than the entire galaxy surrounding it. Quasars, the brightest sustained sources of light in the universe, are powered by matter falling into supermassive black holes. Some quasars are visible from billions of light-years away, which means they're producing the light of trillions of suns. All of that energy comes from gravity, from the curvature of space-time. Matter falling in converts its gravitational potential energy into radiation light before crossing the event horizon. In some cases, up to 40% of the infalling matter's mass energy can be converted into light, which makes black hole accretion one of the most efficient energy production mechanisms in the universe. So light, which bends in black holes' gravity, is also produced by that same gravity with extraordinary efficiency. Now let's talk about how scientists continue to test Einstein's theory in increasingly extreme conditions, because every test either confirms that our understanding is correct or reveals new physics. In September 2015, a century after Einstein published his field equations, the LIGO observatories detected gravitational waves for the first time. Two black holes, each about 30 times the mass of the Sun, spiraled into each other and merged 1.3 billion light-years away. The collision released more energy in a fraction of a second than all the stars in the observable universe combined, and it did so in the form of gravitational waves, ripples in space-time itself. Those waves propagated outward at the speed of light, stretching and compressing space as they passed. When they reached Earth, they changed the distance between LIGO's mirrors by less than 1/10,000th the width of a proton, and LIGO detected it. Here's what's crucial. Einstein's equations predicted gravitational waves in 1916, based purely on the mathematics of curved spacetime. For a century, they remained undetected, leading some to wonder if they were real or just mathematical artifacts. LIGO proved they're real, and their properties match Einstein's predictions exactly. Moreover, gravitational waves travel at the speed of light. This is profound. It means that changes in spacetime curvature, changes in gravity, propagate at the speed of light, not instantaneously. If the Sun suddenly vanished, Earth would continue orbiting for about 8 minutes, the time it takes light to travel from the Sun to Earth before the gravitational waves signaling the Sun's disappearance reached us. In October 2017, LIGO and its European counterpart Virgo detected gravitational waves from two neutron stars colliding. But this time, something unprecedented happened. About 2 seconds after the gravitational wave signal, gamma-ray telescopes detected a burst of high-energy light from the same location. Within hours, optical telescopes observed a bright transient colonova in that region of sky. This was the first time the same cosmic event was observed in both gravitational waves and electromagnetic waves light. And the timing proved something crucial. Gravitational waves and light both travel at exactly the same speed, to within 1 part in a quadrillion. This has enormous implications. Some alternative theories of gravity predict that gravitational waves should travel at different speeds than light. This observation effectively ruled out many of those alternatives in one stroke. Now we need to talk about the elephant in the room, or rather, the microscopic elephant that refuses to fit in the room. Everything I've told you so far about gravity and curved spacetime works brilliantly at large scales: planets, stars, galaxies, black holes. But at the quantum scale, the scale of atoms, subatomic particles, and the fundamental forces of nature's general relativity breaks down. Here's the problem. Einstein's general relativity describes gravity as smooth, continuous curved spacetime. But quantum mechanics, the theory that describes the behavior of particles and forces at the smallest scale, says that everything is fundamentally grainy, discrete, and probabilistic. Light itself is quantum mechanical. Photons are quantum particles, and they exhibit wave-particle duality. When we talk about light bending in curved spacetime, we're treating light as classical electromagnetic waves following geodesics. But at the quantum level, each individual photon is following that path. And quantum mechanics says that a photon doesn't take a single path, it takes every possible path simultaneously until it's observed. This creates a conceptual paradox. If spacetime is curved, and photons follow that curvature, but photons quantum mechanically explore all possible paths, then what determines the correct amount of bending? The answer is that we add up all the possible paths weighted by quantum probability amplitudes, and the result matches what general relativity predicts for the classical path. Quantum mechanics and general relativity give the same answer for light bending, but for completely different reasons. This works fine for weak gravitational fields like those around Earth or even the Sun. But at the center of a black hole, where spacetime curvature becomes infinite at the singularity, both theories give nonsense. General relativity predicts infinite density and infinite curvature. Quantum mechanics says that's impossible because of the uncertainty principle. Something has to give. This is why physicists have been seeking a theory of quantum gravity for nearly a century. We need a theory that describes what gravity is at the quantum scale, where spacetime itself might be made of discrete quantum units. One leading candidate is string theory, which proposes that fundamental particles aren't point-like objects, but rather tiny vibrating strings, and that spacetime has additional hidden dimensions beyond the 3 of space and 1 of time that we experience. In string theory, gravity is carried by gravitons, quantum particles that mediate the gravitational force, just as photons mediate the electromagnetic force. Another approach is loop quantum gravity, which suggests that spacetime itself is quantized, made of discrete loops at the smallest scale, about 10 to 35 meters across, called the Planck length. At this scale, space isn't smooth. It's a seething foam of quantum geometry. Here's what's fascinating. Both approaches suggest that at extremely small scales or extremely high energies, light might not follow exactly the paths general relativity predicts. Photons of different energies might travel at slightly different speeds in quantum spacetime, or they might interact with the quantum structure of space itself. In 2009, the Fermi Gamma Ray Space Telescope observed gamma-ray bursts from explosions billions of light-years away. These bursts contain photons of vastly different energies. Some are thousands of times more energetic than others. If quantum gravity effects exist, higher energy photons might travel slightly faster or slower than lower energy photons. The observations showed that photons of all energies arrived at the same time, to within the measurement precision. This put incredibly tight constraints on quantum gravity theories, ruling out some versions and forcing others to be more subtle. But here's the truly mind-blowing part. We don't know what spacetime actually is at the deepest level. We don't know if it's fundamental or emergent. Some physicists, like Nobel laureate Frank Wilczek, have proposed that spacetime might be an emergent phenomenon, arising from deeper quantum information structures. Like how wetness emerges from countless water molecules, but isn't a property of any individual molecule. If spacetime is emergent, then gravity, the curvature of spacetime, is also emergent. And if gravity is emergent, then the bending of light isn't a fundamental phenomenon, but a consequence of deeper quantum processes we don't yet understand. This raises a profound question. When light bends in a gravitational field, what is really happening at the deepest level of reality? We have Einstein's answer spacetime is curved. We have quantum mechanics answer photons propagate through quantum fields. But we don't yet have the full answer that unifies both perspectives. Everything we've discussed so far assumes we understand what mass and energy are. But here's a revelation that will shake everything. We don't. At least, not most of it. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma galaxy cluster, measuring how fast galaxies were moving within it. He used Newton's laws, and later, Einstein's equations give the same result to calculate how much mass the cluster must contain to keep those galaxies bound together at those speeds. The answer shocked him. There wasn't nearly enough visible matter stars and gas to account for the gravitational effects he observed. He proposed that the cluster must contain large amounts of dunkel materie, dark matter, that doesn't emit light but does exert gravity. For decades, this idea was largely ignored. Then in the 1970s, American astronomer Vera Rubin studied the rotation curves of galaxies. She measured how fast stars orbit at different distances from the galactic center. Basic physics says that stars farther out should orbit slower, just like planets farther from the sun orbit slower. But that's not what Rubin found. Stars at the outer edges of galaxies were moving just as fast as stars closer in. The only way to explain this was if galaxies were surrounded by enormous halos of invisible matter, dark matter, extending far beyond the visible stars. Today, thanks to gravitational lensing, we can map dark matter directly. Remember, gravitational lensing depends on total mass, not just visible mass. When we observe how light bends around galaxy clusters, we can reconstruct the mass distribution creating that bending. The results are unambiguous. About 85% of the matter in the universe is dark matter. We can see its gravitational effects. We can see how it bends light, but we don't know what it is. It doesn't interact with electromagnetic radiation at all, which means it's completely invisible. It only interacts through gravity. Think about that. When light bends around a galaxy cluster, most of that bending is caused by matter we cannot see, made of particles we haven't identified, governed by physics we don't fully understand. We only know it's there because of how it curves spacetime, which we only know because light bends. But dark matter isn't the strangest thing in the universe. That honor goes to dark energy. In 1998, two teams of astronomers were measuring the expansion rate of the universe by observing distant supernova stellar explosions that serve as standard candles with known brightness. By comparing their apparent brightness to their known intrinsic brightness, astronomers can calculate their distance. By measuring their redshift, astronomers can determine how fast they're moving away from us. Both teams found something impossible. Distant supernova were fainter than expected, which meant they were farther away than they should be if the universe were simply expanding at a steady rate or slowing down due to gravity. The expansion of the universe wasn't slowing down. It was speeding up. This discovery won the Nobel Prize in Physics in 2011, and it revealed that about 70% of the energy content of the universe is dark energy, a mysterious component that acts like anti-gravity, pushing space apart. Dark energy curves space-time too, but in the opposite sense from matter. Where matter creates attractive gravity, pulling things together and causing space-time to curve inward, dark energy creates repulsive gravity, pushing things apart and causing space-time to curve outward. This means that light traveling across the universe isn't just bending due to matter and dark matter. It's also being affected by dark energy's influence on the expansion of space itself. Photons traveling across billions of light years are being stretched, their wavelengths increased as the space they're traveling through expands. This is cosmological redshift, and it's distinct from both Doppler redshift, caused by motion, and gravitational redshift, caused by climbing out of gravitational wells. It's caused by the expansion of spacetime itself, driven primarily by dark energy. Here's the humbling reality. When we see distant galaxies and measure their redshifts, we're seeing light that has traveled for billions of years through expanding space, bent by the gravity of countless galaxies and dark matter halos, all while the universe's expansion was accelerating due to dark energy. That light carries information about the entire history and structure of the cosmos. And we only see about 5% of what's out there. The rest 95% of the universe is dark matter and dark energy, invisible to light, known only through gravity's effect on space-time curvature. This brings us back to our original question. Why does gravity bend light? The full answer is that mass energy, including forms we haven't identified, curves space-time, and light follows geodesics through that curved spacetime. But we're missing most of the picture. Most of what's curving spacetime is a mystery. Before we move toward how all this affects you personally, I need to tell you about one more mind-shattering consequence of light, bending that changes how we perceive the entire universe. When you look up at the night sky, you see stars and galaxies in specific positions. But here's what you need to understand. Almost nothing is where it appears to be. You're looking at a cosmic illusion created by curved spacetime. Every massive object between us and distant light sources bends that light. The Milky Way galaxy's mass distribution curves spacetime, shifting apparent positions of distant galaxies. The sun's gravity deflects starlight, which is what Eddington measured. Earth's gravity does it too, though the effect is tiny. But it gets stranger. Light travel time means we see distant objects as they were in the past. The Andromeda galaxy is 2.5 million light-years away, so we see it as it was 2.5 million years ago. The most distant galaxies we've observed are so far away that we see them as they were when the universe was less than 3% of its current age over 13 billion years ago. Now combine this with gravitational lensing. When we observe highly magnified galaxies behind massive galaxy clusters, we're seeing them both as they were billions of years ago, and with their positions and shapes distorted by intervening mass. We're not seeing where they were. We're seeing where the light path through curved spacetime makes them appear to be. In some cases, we're seeing the same galaxy in multiple locations, simultaneously different images created by light taking different paths around the lensing mass. Which image shows the real position? Neither. Both. The question doesn't make sense because position itself is observer-dependent in a universe where spacetime is dynamically curved. Here's an even deeper issue. We often talk about the universe being 13.8 billion years old and 93 billion light-years across. But those numbers assume a specific definition of space and time, a specific way of slicing space-time into space and time components. In general relativity, there's no unique way to do this. Different observers moving at different speeds or in different gravitational fields would slice space-time differently and get different answers for how big is the universe right now. The concept of now across cosmic distances is ambiguous. When we say the universe is a certain size right now, we're using a particular convention called comoving coordinates, where now is defined by the cosmic microwave background radiation's temperature being the same everywhere. But this is a choice, not a fundamental truth. Light's finite speed combined with space-time curvature means that causality, the relationship between cause and effect, has a structure that's fundamentally different from our everyday intuition. You can only influence or be influenced by events that are within your light cone, the set of events that light could reach from you, or that could send light to reach you. Your past light cone consists of all events that could have causally affected you, all the points in spacetime from which light could have traveled to reach you at this moment. Your future light cone consists of all events you could potentially affect, all the points in spacetime to which light leaving you now could eventually travel. Massive objects warp these light cones. Near a black hole, your future light cone tilts inward. Far from any mass, your light cones are symmetric and extend indefinitely. The structure of causality itself is determined by gravity's effect on light. Now here's where your brain should really start hurting. If light defines causality and gravity bends light, then gravity determines what can cause what. The causal structure of the universe, which events can affect which other events, is determined by the distribution of matter and energy curving spacetime. In principle, if you could manipulate spacetime curvature enough, you could create closed time-like curves paths through spacetime that loop back on themselves, allowing time travel. Most physicists think such configurations are either impossible or unstable, but Einstein's equations technically allow them in certain extreme situations, like the interior of rotating black holes or near cosmic strings, hypothetical one-dimensional defects in spacetime. The fact that we can even discuss time travel mathematically, using the same equations that predict GPS satellite time dilation and gravitational lensing, shows just how strange general relativity is. Time is not absolute. Space is not absolute. The speed of light is absolute, and it defines the structure of cause and effect throughout the cosmos. Let's take a step back and confront what all of this means for how we understand reality itself. I've been throwing around phrases like curved spacetime and geodesics as if they're answers, but they're really just increasingly sophisticated ways of describing what we observe. They don't answer the deepest question. What is spacetime fundamentally? Here's what keeps physicists awake at night. Spacetime in general relativity is treated as a smooth, continuous manifold, a mathematical object that's infinitely divisible. But quantum mechanics tells us that at the smallest scales, everything is discrete and probabilistic. These two foundational theories of modern physics are mathematically incompatible. When we say gravity bends light, we're glossing over this incompatibility. At the scales we can observe, from atomic scales up to cosmic scales, the incompatibility doesn't matter. General relativity's predictions work. Quantum mechanics' predictions work. Light bends exactly as Einstein predicted. But at the Planck scale, about 10 to 35 meters and y-43 seconds, both theories break down. At these scales, quantum fluctuations in spacetime itself should become important. Space and time might not be continuous, but quantized into discrete units. The smooth curved spacetime of general relativity might be an approximation, like how a sandy beach looks smooth from a distance, but is made of discrete grains up close. If spacetime is quantized, then the path of a photon isn't a smooth curve through curved spacetime. It's something more complex, a quantum superposition of paths through a foamy, fluctuating quantum geometry. The fact that this quantum craziness averages out to give us Einstein's clean predictions is remarkable, but it also tells us we're missing something fundamental. Some theoretical physicists have proposed even more radical ideas. What if spacetime isn't fundamental at all? What if space and time emerge from something deeper, perhaps from quantum entanglement between fundamental degrees of freedom that aren't spatial or temporal? This idea, called emergent spacetime, suggests that asking, "What is spacetime made of?" is like asking, "What is temperature made of?" Temperature isn't made of anything. It's an emergent property of molecular motion. Similarly, spacetime might be an emergent description of quantum information relationships. If this is true, then gravity and the bending of light aren't fundamental either. They're emergent phenomena arising from deeper quantum information dynamics. Just as thermodynamics emerges from statistical mechanics, general relativity might emerge from quantum information theory. Nobel laureate Gerard T. Hooft and Leonard Susskind developed the holographic principle, which suggests that all the information in a volume of space can be described by information on the boundary of that region. This bizarre idea arose from studying black holes. The amount of information a black hole can contain is proportional to its surface area, not its volume. This led to even more radical proposals. Maybe the three-dimensional universe we experience is itself a holographic projection of information encoded on a distant, two-dimensional boundary. Maybe the entire cosmos, including the paths light takes through curved spacetime, is a hologram. These aren't just wild speculations. They're attempts to reconcile the deepest truths we've discovered about reality, that quantum mechanics describes information and probability at the fundamental level, that general relativity describes geometry and causality at large scales, and that these two descriptions must ultimately be aspects of a single, unified truth. Here's what this means for our question about why gravity bends light. We have a phenomenologically perfect answer. We know that light follows geodesics in curved spacetime. We can calculate those paths with extraordinary precision, and every observation confirms the predictions. But we don't yet know what spacetime is at the deepest level. So in some sense, we don't fully understand what light bending really is. It's like knowing that water boils at 100 degrees Celsius without knowing what water molecules are. The description works, but there's a deeper truth waiting to be uncovered. Now let's bring this home. Let's talk about what all of this means for you, personally, right here, right now. You might think that curved spacetime and gravitational lensing and black holes are abstract concepts relevant only to astrophysicists studying distant cosmic phenomena. But here's the truth. You are living in curved spacetime right now. Your existence is shaped by these effects every moment of every day. The GPS on your phone works because engineers understood that time passes differently at different heights in Earth's gravitational field. Every time you use navigation, you're relying on corrections for general relativistic time dilation. You're using Einstein's insights about curved spacetime to navigate your curved Earth. The atoms in your body, the molecules that make up your cells, are held together by electromagnetic forces, the same forces that create light. The photons bouncing around inside your eyes right now, creating your visual experience, are following paths through the curved spacetime created by Earth's mass. You are literally seeing through curved spacetime. The sun, which powers nearly all life on Earth, generates its energy through nuclear fusion. That process converts mass into energy according to Einstein's equation E equals mc. The sunlight reaching Earth the energy that grew the food you ate, that warmed your skin, that drives weather patterns, is energy that was once mass, now traveling through curved spacetime to reach you. And here's something more profound. You are made of atoms that were forged in the cores of ancient stars. Every carbon atom in your body, every oxygen atom, every atom heavier than hydrogen and helium, was created by nuclear fusion in stars that exploded billions of years ago as supernova. Those explosions sent atoms flying through space, where they eventually coalesced into new star systems, including our sun and planets, including Earth, including you. The light from those ancient supernova traveled through the universe's expanding, curved spacetime. Some of it may still be traveling, bent around galaxy clusters, creating gravitational lenses we observe today. You are literally made of stardust, and the journey that stardust took to become you was guided by the curvature of spacetime. But there's an even deeper connection. You are not separate from spacetime. You are part of it. Your mass curves the spacetime around you. It's an infinitesimal effect. Your gravitational field is unimaginably weak, but it's real. You are warping the fabric of reality simply by existing. Every movement you make, every breath you take, shifts the curvature of spacetime around you. Light passing near your body bends slightly due to your gravitational field. The effect is far too small to measure, but it's predicted by the same equations that predict black holes and gravitational waves. You and a black hole are playing by the same rules, you're just playing at vastly different scales. Here's what I want you to understand. The universe isn't something that exists out there, separate from you. You are a pattern in the universe's fabric. Your thoughts are electrochemical processes powered by energy that was once mass in a star's core. Your perceptions are constructed from photons that have traveled through curved spacetime to reach your eyes. Your very existence is a temporary configuration of matter and energy, following the geodesics of spacetime from the Big Bang toward the universe's ultimate fate. When you understand that light bends in gravitational fields, not because it's being pulled, but because spacetime itself is curved, you're understanding something profound about reality's nature. There is no absolute space or time. There is only spacetime, a unified fabric that's flexible and dynamic and responsive to energy and matter. You're not living in space and time. You're living as a pattern in spacetime. This should change how you see yourself. You're not a separate thing in a universe. You're a temporarily organized process through which the universe knows itself. The atoms in your brain, arranged in patterns that create consciousness, are the universe becoming self-aware. When you look up at a distant star, photons that left that star years or centuries ago, traveling through the curved spacetime of our galaxy, enter your eye and trigger neural signals that create the experience of seeing starlight. You and that star are connected by those photons' journey through spacetime. You're participating in the universe's causal network, the web of light and matter and curved geometry that connects everything. We've covered an enormous amount of territory, from Eddington's eclipse expedition to black holes, to quantum gravity, to your personal connection to curved spacetime. But I want to be honest with you about what we still don't know, because the boundaries of knowledge are where the most exciting questions live. First, we still don't know what dark matter is. Multiple experiments are underway trying to detect dark matter particles directly. Deep underground laboratories shield detectors from cosmic rays, hoping to catch the rare interaction of a dark matter particle with normal matter. So far, nothing definitive. Either dark matter interacts even more weakly than we thought, or it's something we haven't imagined yet. Some physicists have proposed alternatives to dark matter modifications to gravity itself that would eliminate the need for invisible matter. These theories, called modified Newtonian dynamics, MOND, and its relativistic extension, have had some successes in explaining galaxy rotation curves, but they fail to explain gravitational lensing observations. These observations will test general relativity in the most extreme conditions. Do black holes behave exactly as Einstein's equations predict? Are there deviations that hint at quantum gravity effects? Can we observe the photon ring structure in exquisite detail? These observations might reveal new physics. Fourth, understanding gravity and spacetime might enable technologies that sound like science fiction today. If we could manipulate spacetime curvature, we could theoretically create warp-drive spacecraft that compress space ahead and expand it behind, moving faster than light relative to distant observers without locally exceeding light speed. This remains speculative, requiring exotic matter with negative energy density, but it's not forbidden by known physics. Even without warp drives, precise control of gravitational fields could enable ultra-efficient propulsion, communication systems that use gravitational waves instead of electromagnetic waves, or computational devices that exploit curved spacetime to solve problems. Fifth, the coming decades will likely see breakthroughs in quantum gravity. New experimental tests are being designed. The LIGO detectors might be sensitive enough to detect quantum gravitational effects in their mirror's motion. Tabletop experiments using ultra-cold atoms or levitated nanoparticles might probe the interface between quantum mechanics and gravity. Space-based experiments testing the equivalence principle to unprecedented precision might reveal subtle violations hinting at new physics. If we achieve a working theory of quantum gravity, it could be as revolutionary as quantum mechanics was in the 20th century. Quantum mechanics gave us semiconductors, lasers, GPS, MRI, nuclear power, and much of modern technology. Quantum gravity might unlock technologies we can't currently imagine. Now, I want to address something personal. Throughout this journey, we've scaled up and down through reality, from the Planck scale to the cosmic horizon, from the quantum foam of space-time to the largest structures in the universe. Where do you fit in all of this? Here's a perspective that might help. The human scale, your size, your time scale, your energy scale, is roughly logarithmically halfway between the smallest and largest scales we know. The Planck length is about y minus 35 meters. The observable universe is about yd meters across. The geometric mean is around 10 to 4.5 meters, about a millimeter. You're within a few orders of magnitude of the middle. Similarly, the shortest meaningful timescale is the Planck time, about 10 to 43 seconds. The age of the universe is about y seconds. The geometric mean is around 10 to 13 seconds, about the timescale of molecular vibrations. Your lifetime of a few billion seconds puts you a bit toward the cosmic end, but still roughly in the middle range. You are not too small or too large, too fast or too slow. You're at a scale where you can potentially understand both the quantum realm and the cosmic realm. Your brain, consisting of about 1,011 neurons making about Y connections, is complex enough to model the universe's structure, from quarks to galaxy superclusters. Think about that. The universe has arranged matter into a configuration, that can understand how the universe works. The atoms in your brain, following the laws of physics, create thoughts about those laws. This is what consciousness is, the universe modeling itself. When you look at a gravitational lens image showing a distant galaxy warped into arcs and rings, you're seeing light that traveled billions of years through curved spacetime to reach your eye. That light triggers neural signals in your visual cortex, creating the experience of seeing. But more than that, your prefrontal cortex interprets that image, understanding what created it. Spacetime curvature by intervening mass. You're not just seeing, you're comprehending. This comprehension is rare in the universe. Most matter exists as diffuse gas, cold dust, or plasma, in stars unconscious, unaware. Only in rare pockets, on planets like Earth, does matter organize into life, and even more rarely into conscious, intelligent life capable of understanding cosmology and fundamental physics. You are one of those rare configurations. You are how the universe has come to understand that light bends in gravitational fields, that spacetime is curved, that reality is far stranger than everyday experience suggests. Now, you might feel insignificant in the face of cosmic scales. How can one human matter in a universe of Y stars, spanning 93 billion light years, existing for 13.8 billion years? But here's a different perspective. Significance isn't about size or duration. It's about complexity, consciousness, and meaning creation. A single human brain is more complex than any star or galaxy. Stars are huge, but simple, mostly hydrogen fusing into helium. Galaxies are vast, but their large-scale structure is relatively straightforward matter following gravitational dynamics. Your brain contains more synaptic connections than there are stars in thousands of galaxies. The electrochemical patterns in your neural networks create thoughts, emotions, memories, dreams, understanding. You create meaning. You experience beauty when looking at a gravitational lens image. You feel awe contemplating curved spacetime. You're not just a pattern of atoms. You're a pattern that knows it's a pattern. In the entire observable universe, we found exactly one planet where this definitely happens. Earth. We don't know how common consciousness is. There might be countless alien civilizations, or we might be alone. Either way, consciousness is rare and precious. Your existence, your awareness, your ability to understand these concepts, these are cosmically significant. When you grasp that gravity bends light because space-time is curved, you're achieving something that took the universe 13.8 billion years to accomplish. A piece of the universe understanding its own fundamental nature. We've been on an incredible journey together, and now I want to tie everything together with a revelation that will reframe everything we've discussed. Here's what I want you to understand at the deepest level. The question, why does gravity bend light if light has no mass, isn't just a physics question. It's a question about the nature of reality itself. And the answer reveals something profound. Reality is not made of things moving through space and time. Reality is made of relationships in space-time. Let me explain what I mean. We grow up thinking of the world as made of objects, tables, chairs, people, planets, stars that exist in space and move through time. These objects have properties like mass, charge, and momentum. Forces act on them, causing them to accelerate. This is the Newtonian worldview, and it works brilliantly for everyday experience. But Einstein revealed that this is just an approximation, a useful fiction for slow speeds and weak gravitational fields. At a deeper level, there are no objects moving through space and time. There's only space-time itself, a four-dimensional fabric with geometry that's determined by the distribution of energy and momentum. What we call objects are actually patterns in fields: the electromagnetic field, the electron field, the quark field, and so on, and these fields exist in space-time. What we call motion is actually those patterns tracing world lines through space-time. What we call forces are actually the geometry of space-time, telling those patterns which world lines to follow. A photon isn't a little particle flying through space. It's an excitation in the electromagnetic field, a ripple propagating through space-time. That ripple doesn't have mass, but it has energy and momentum, and it follows geodesics, the straightest possible paths through space-time. When space-time is curved, those geodesics are curved, and we observe this as light bending. But here's the deeper revelation. The photon doesn't exist independently of space-time. The photon is a feature of space-time. It's like asking why a wave on the ocean bends when it encounters a current. The wave isn't separate from the water. It's a pattern in the water. Similarly, light isn't separate from space-time. It's a pattern in the electromagnetic field embedded in space-time. Everything is patterns in fields, and fields exist in space-time. And space-time's geometry is determined by energy and momentum, creating a self-consistent, interconnected whole. You can't separate light from space-time and ask why one affects the other. They're aspects of a unified reality. This is why Einstein called his theory general relativity. The relativity isn't just about relative motion. It's about the relational nature of reality itself. Nothing has absolute properties. Everything is defined by its relationships to other things. Your position is relative to other objects. Your simultaneity with distant events is relative to your motion. Your time rate is relative to your gravitational field. Even space-time geometry is relational. It's determined by matter and energy, which in turn follow paths determined by that geometry. Now here's where this gets truly mind-blowing. If reality is fundamentally relational, then asking what is space-time made of might be the wrong question. Space-time might not be made of anything. It might be the structure of relationships between events, between field values, between quantum degrees of freedom. Some theoretical physicists are exploring this idea through quantum information theory. They're proposing that the fundamental reality is quantum information entanglement relationships between quantum systems, and that space-time emerges from those relationships. In this view, space and time aren't fundamental. They're emergent descriptions of quantum information structure. If this is true, then gravity bending light is an emergent phenomenon arising from deeper quantum information dynamics. The curvature of space-time, the paths that photons follow, even the distinction between light and space-time, all of it emerges from quantum information relationships. This brings us to perhaps the most profound implication. If space-time is emergent, then the universe we observe, with its galaxies, stars, planets, and conscious beings, is an emergent phenomenon. The patterns we call atoms emerge from quantum fields. The patterns we call molecules emerge from atomic interactions. The patterns we call life emerge from molecular complexity. The patterns we call consciousness emerge from neural dynamics. You are an emergent pattern at the highest level of complexity we know. And because you're made of the same quantum fields and follow the same laws as everything else, when you understand how light bends in gravitational fields, you're not learning about something external to you. You're experiencing the universe's self-understanding. Let me make this concrete. Right now, photons are entering your eyes from your screen